Alright, welcome back. This is lecture 7 in this course on mathematical tools. The topic of this lecture is graphs of inverse functions. Now in the previous lecture, at the end of the previous lecture, I posed a question that do you see any relationship between the graph of an inverse function and the graph of the original function. So graph of f of x and the graph of f inverse x. Do you see any relationship? Now you can hold on to your answer because now we are going to explore that using, let's say, slightly simpler functions first and then more complex functions. Okay. So what we will do, we will take some examples, we will derive the inverse function and then we will draw the graph of the function f of x and its inverse function on the same xy plane. Okay. So let us begin with a simple linear function. So let us say f of x equals to 2x plus 1. Let's say this is the function. Okay. First, let us find the inverse of this function. We will follow those three steps. First, replace f of x by y. So you get y equals to 2x plus 1. This is the equation you get. Now solve this equation for x. Okay. So this is step 1. Step 2, solve this equation for x. How do we do that? 2x equals to y minus 1, x would be equal to y minus 1 by 2. So this is we have done. Now in step 3, we just replace this, we just change the variables. The form remains the same, we just change the variables such that this looks like an inverse function. So we replace x by f inverse x and we replace y by x. Okay. So this is the inverse function of this particular function f of x equals to 2x plus 1. Now in both these functions there is no problem, they can take all real values. So the domain and codomain would be set of all real values. So x can take all real values, y can take all real values in both function as well as inverse function. Okay. So let us draw their graphs. This is the y-axis line and let's say this is the x-axis line I'm plotting here. So first I will plot the original function using blue ink. Okay, what is the original function? F of x equals to 2x plus 1. Let me plot this. Now at x equals to 0, value of this function is 1. At x equals to 1, the value of this function is 3. Okay, so somewhere here. At x equals to 2, the value of this function is 5. Somewhere here. Okay, so this is a straight line, right? You know this is an equation of a straight line. This is how it would look like. It would extend in both directions like this. So this is the graph of the function f of x equals to 2x plus 1. Now let us draw the graph of the inverse function using red ink. What is the inverse function? X minus 1 by 2. So what would be the value of this function at x equals to 0? So when x is 0, the value of this function would be minus 1 by 2. Okay, so x equals to 0, the value of this function would be minus 1 by 2, somewhere here. And at x equals to 1, the value of the function is 0. Okay, so the function is 0 here. Okay. Oh, sorry. So the function is 0 somewhere here. Okay, and at x equals to, let's say 2, the value of function is 1 by 2. So when x is 2, the value of function is 1 by 2. So somewhere here. So it would be also a straight line. The slope of the line is 1 by 2, right? So this is actually not as steep as this line. This line is slope 2, but this line is a smaller slope. 1 by 2, right? So it would look something like this. If you draw, I mean, if you can draw all other points as well. So this would look something like this. Okay, so they would look diverging in this quadrant, right? These are called quadrants, by the way. This is first quadrant, second, third, fourth. Idea is this: this is x is positive, y is positive here. Okay, here x is negative, y is positive. Here both are negative. Here x is positive and y is negative. So this is how the graphs look like. And they keep on, the distance keeps on increasing in the first quadrant. Why does that happen? Because the blue line has higher slope. So the blue line is more steep and the red line is slightly flatter. Okay, so red line grows slowly, the blue line grows very fast. Okay, so that's why blue line has much larger values of y corresponding to those values of x. Red has much smaller values of y corresponding to those values of x, right? So this is how this graph would look like. Now try to answer the question. So do you see any relationship between these two graphs? Any symmetry or any sort of graphical properties? Okay. Now it turns out that there is a very interesting relationship between the inverse function and the graph of the original function, which is this: that if you draw a line called y equals to x, basically a line with this equation. So if you put a mirror, so let's say you put a mirror on this line y equals to x, okay, then the inverse function, graph of the inverse function, is a mirror image of the graph of the original function. Okay, what does that mean? If you put a mirror here, let's say, and you get the graph, this graph, okay, then the inverse graph would look exactly like this on the other side. So the inverse graph is symmetric around this y equals to x line. Once you know the graph of the function f of x, you can always draw the graph of the inverse function, because you know exactly how it would look like. You just need to draw a line y equals to x and then just figure out what its mirror image would be, right? So for example, one property that would happen is that, let's say the line, your graph has this much distance from this mirror line y equals to x, the inverse graph would also have this much distance. That means in this area where your blue line is far from your y equals to x line, the inverse function line would also be far from y equals to x. And here in this area where blue line is close to y equals to x, this red line would also be close to y equals to x. So that's the idea. So your inverse graph is actually a mirror image of your original graph along y equals to x line. So if you place a mirror on y equals to x line. So this is the relationship between graphs of inverse function and the original function. Let us try some more examples. So let us say the function is f of x equals to x square plus 2x plus 3. Okay, let's say this is the function. Now let's take, okay, this is fine. Let's say this is the function. Now let us try to find the inverse of this function first. So to find inverse, step 1, replace f of x by y, x square plus 2x plus 3. Now how do we solve this for x? What would be x as a function of y? Okay. So now this won't be straightforward, right? Let us take slightly simpler function just to begin with. You can take this example later on. Let's say it's x square plus 3. So y equals to x square plus 3. Okay. Now you can try to solve it for x. X square would be y minus 3. X would be square root of y minus 3. Okay, this is how it will look like. And this thing can be both positive, negative. So x can take both as positive as well as negative values, right? Now I can write it in the form of an inverse function. So f inverse x equals to plus minus x minus 3. Okay. What are the domains and codomains here? So for the original function x squared plus 3, x can take all real values, totally fine. What possible values y can take? Well, because x square has to be greater than equal to 0, y has to be greater than equal to 3, right? So the codomain was y greater than equal to 3. The same thing would happen here. Here, the domain would become like this: x has to be greater than equal to 3. And what values y can take? Y can take any real value. Okay, basically f of f inverse x, the output can take any real value. That's the idea. Now let us draw the graph of this original function and the inverse function. This is xy plane. I will draw the graph of original function using blue. It's x squared plus 3 at x equals to 0. Value of y is 3. If x is 1, y is 4. Okay. If x is minus 1, y is 4. So it's symmetric around y axis, right? And it would increase very rapidly because it's x square term. So if you take x equals to 2, then the value of y becomes 7. So very large value at 2. So the graph would look something like this. Okay, so this is the graph of x squared plus 3. Let us try to draw graph of f inverse x, which is square root x minus 3. Now first let us predict it using our idea that if you place a mirror along y equals to x, then the inverse would be mirror image along this graph. So how the mirror image would look like along this graph? It would be something like this. So where this graph cuts the y-axis, this graph would cut the x-axis. So at y equals to 3, it would cut at x equals to 3. Also, x cannot take values less than 3. It has to be greater than 3. So the graph would look something like this. I'm just taking the mirror image. If you are really not sure, you can literally place a mirror and see what would happen. So here, this would look something like this. Okay, so whatever happened on the y-axis here, it would happen on the x-axis here. Sorry. Okay, so this is the graph of x minus 3. So it can take negative values as well. And you can verify this. So let us plug in x equals to 3, then the value of this function would be 0. If x is, let's say, slightly greater than 3, let's say 4, okay, then the value of y could be 4 minus 3, 1. Okay, the square root of 1 is 1, but it could be plus as well as minus. So basically both values like this. If you have x equals to 4 here, okay, so corresponding value would be 1 minus 1 like this. Similarly, when x is, let's say, 7, then 7 minus 3, let's say x is 7 here, somewhere here, x minus 3 would be 4, square root of 4 is 2 plus minus 2. So it can take 2 as well as minus 2. This is how this looks like. Okay, so we have drawn the graph of the function x squared plus 3 and its inverse function plus minus root x minus 3. Okay, and you can check domain and codomain. So here y has to be greater than equal to 3, here x is greater than equal to 3. So basically mirror image is such that whatever happened on the y-axis here happens on the x-axis here. Okay? That's the idea of inverse function as well. Let us try some more functions. Maybe you can try a cubic function, right? So let's say, no, not cubic, let's say some function of this form. Let's say f of x equals to 1 by x. Okay? F of x equals to 1 by x. Now, what is the domain? X cannot be equal to 0. What is the codomain? Y also cannot be equal to 0. Okay. Let us drive the inverse function. So, step 1, y equals to 1 by x. X would be 1 by y. So, actually here inverse function is same as the original function. So, f inverse x equals to 1 by x. So, you have same function, original function as well as inverse function, right? Only thing that is changing here now, x, so that is also same, x can't be equal to 0, y can't be equal to 0, right? So, domain and codomain also remains the same. Now, let us try to draw these two. So, what is the graph of the function 1 by x? So, when x is 0, graph is undefined. When y is 0, graph is undefined. When x is 1, the value of y is 1. So, when x is 1, y is 1. So, somewhere here. When x is 2, y is 0.5, like this. When x is 3, y is even a smaller value. So, the value of y is decreasing as the positive values of x are increasing. But what if x is very, very close to 0 and has a very small value close to 0, let us say 0.0001, then the value of y is very large. So, the graph would look something like this. Sorry. Okay. How about negative values of x? If x is negative but very, very close to 0, let us say minus 0.001, then y would have a very large negative value. Okay. So, on this side, the graph would look at x equals to minus 1, y would be minus 1. So, this point would be remain here. So, this graph would look something like this on this side. Okay. Good. So, this is graph of 1 by x. Now, interestingly here inverse function has the same form. Okay. Why is that? Let us see. If you draw this mirror y equals to x, what you see is that the graph that you are seeing is already a mirror image of itself, right? So, this graph is already symmetric around y equals to x. So, if you try to draw a graph which is a mirror image of this existing blue graph, the red graph would exactly be same as blue graph, right? So, the red graph would look exactly same. So, because this red line is a mirror image of this one and this here is a mirror image of the upper line. Similarly, here this is mirror image of this and this is mirror image of this. Okay. So, that is why function inverse function graph would look exactly same, because the function inverse function are also same. That is the region. How about, well, we already tried slightly complicated function. So, how about we try something like f of x equals to 1 divided by, let us say, x square minus 1. Okay. So, this is the original function. Now, can you figure out the domain and codomain? Now, x square minus 1 cannot be equal to 0, x square cannot be equal to 1. That means x cannot be equal to 1 and x cannot be equal to minus 1. Okay. And similarly, codomain would be y equals to 1 by x square minus 1. X square minus 1 is 1 by y. X square is equals to 1 plus 1 by y. Now this x square has to be greater than equal to 0. So 1 plus 1 by y is greater than equal to 0. That means first y cannot take 0. Okay. Second thing, the only way this can be greater than equal to 0 is something like this. So let's say 1 by y is less than equal to 1. This is one way, right? Can it be greater than 0 if y takes negative value? Not really, right? If y takes some negative value such that this 1 by y remains less than equal to, I don't know, yeah, if it remains, let us try. So if, what if it takes a large negative value? Okay, yeah, this is fine. So it's 1 minus some very small value. Yeah, this would be greater than equal to 0. Yeah, so this is fine. So only constraint is this, that y can't be equal to 0. Okay, but and 1 by y has to be less than equal to 1, and that implies that y should be greater than equal to 1, or y can take a negative value such that if it is greater than minus 1, let's say minus 0.99, then 1 by y would become 1 by 0.099. Okay, so this is 100 by 99. Okay, now this is negative, so this won't work. So y has to be less than equal to minus 1. Okay, so these are the conditions for y. If it is less than equal to minus 1, then this would hold. If it is greater than equal to 1, then this will hold. So basically the codomain is like this: greater than equal to 1, less than equal to minus 1. Okay, so there are no values of y between 1 and minus 1. Okay, it's interesting because if the value of y is 0.01, that should work, right? Okay, so let's say y is greater than 0, because y can't be equal to 0. So y is greater than 0 and y is less than equal to minus 1. Yeah, I think this is fine. All right, so if y has some positive value, then it is fine. If y has a large negative value, then it is fine. Basically large negative value in such a way that it is less than minus 1, less than or equal to minus 1. Okay, anything between minus 1 and 0 would be undefined. So this is how we worked out the domain and codomain. The function was f of x equals to 1 divided by x square minus 1. Let us find the inverse of this function. Okay. To find inverse, I will write 1 by x square minus 1. That means x square minus 1 would be 1 by y. X square equals to 1 by y plus 1. X equals to square root 1 plus 1 by y plus minus, right? I can write it in the form of an inverse function, plus minus 1 plus 1 by x. Okay, so this is the inverse function. Now let us draw the graph of f of x equals to 1 by x square minus 1. Now the domain and codomain would see reverse, by the way. So x has to be now greater than 0, either greater than 0. So that means x is positive. So that way inside square root you would have positive value. Another way in which you can have positive value inside square root is x square less than equal to minus 1. Okay, so that's the domain. So this codomain becomes the domain. And what would be codomain? We already saw the codomain here, which is that x can't be equal to 1 minus 1. So in this case, y cannot be equal to 1, y cannot be equal to minus 1. So let us try to draw the graph of this function, 1 by x square minus 1. So x here domain is x can take any value except 1 and minus 1. So we can draw those lines at x equals to 1 and minus 1. Let's say here is 1, here is minus 1. Fine. It's not very straight, but might work for us. Okay, so let's say x equals to 1 is here. This is x equals to 1. Let's say this is x equals to minus 1. Okay. Let's draw the other values. When x is 0, the value of y is minus 1. So here. And when x is minus 1, no, then it's undefined. If x is, let's say, close to 0, let's say 0.001 on the positive side, then x square would be a very small positive value. And if you subtract minus 1 from it, it would remain minus 1. So this thing would remain close to minus 1. But in the denominator, you don't have exactly minus 1, but a value slightly lesser than minus 1. So that means the value of y would be slightly greater than minus 1. Okay. So this increases. Okay. Now, and that makes sense because if you look at y has to be less than equal to minus 1 or greater than 0. So y cannot have value between in this region between minus 1 and 0. And when we draw closer to 1, let's say you have 0.99999, then if you subtract it from 1, then it remains a negative value, but it would be a very small negative value in the denominator. Let's say minus 0.0001. That means a very large negative value overall, right? So basically the graph goes like this. Okay. And it should go in the same way in both directions. Similarly, in this direction, because you have x square term, the graph also goes like this. Okay. What happens in these upper quadrants? Now, if you take x slightly, if let's say x is slightly greater than 1, okay, 1.001 minus 1, 0.0001 positive, that means a large positive value. So here it is some large positive value close to 1. But if x is very, very large, then it would be close to 0. So something like this. Maybe it would be more steep. Okay. Similarly, on this direction, it would look something like this. Okay. So this is the graph of this function. Okay. Now, what would be the graph of inverse function? Now, in order to find inverse, let us draw a line y equals to x here and try to figure out how it would look like as a mirror on this line, right? So let us begin with this. What would be mirror image of this graph? Well, in order to find mirror of this graph, let us plot these lines y equals to 1 and at y equals to -1, because the domain and codomain would reverse now. Okay, so the mirror image of this line, which is asymptotic at x equals to -1, now mirror image would be such that a line which is asymptotic to y equals to -1, okay, and it would go in this direction like this. Sorry, it would go something like this. Now this is mirror image of this. Similarly, what would be mirror image of this one? This is asymptotic at x equals to 1. This would look like this. Okay, and you can also see these are also mirror image of each other along this line. Okay, now what about these lines? This is coming off here, so the mirror image of this line, this blue line, would be on this axis here at x equals to -1, and it would look like this. You may find it confusing, but just try to apply yourself and you will find out a way. Basically, the x-axis and y-axis are reversing. So whatever was happening on y-axis here, I'm doing it on x-axis here. So it was all negative y values, now it's all negative x values. Okay. Oh, sorry, I think this line is not correct, because this is not mirror image of this one. Sorry. So this is mirror image of this one. Fine. And what would be mirror image of this one along this line? Actually, it would remain similar. It would remain in this quadrant. So let us see. So mirror image of this line would be, yeah, like this. Sorry. Yes, like this. So this red and this blue, these are mirror images of each other along this line, right? So whatever was happening on y-axis here is happening on x-axis here. Right? So this is for example, this part is mirror image of this part, and this part is mirror image of this part. Yeah. This is how they are symmetric around y equals to x. Okay, so if you just focus on these red lines, this is how the graph looks like. So all everything here in this quadrant, so this is basically allowing all negative values of x less than equal to -1. This is how it looks like. And on this side, basically nothing is allowed in this region between x equals to -1 and x equals to 0. And this is how the graph looks like on the other side. Okay, and this graph would be symmetric. The graph of this inverse function f inverse x is symmetric around x equals to 0 line, basically the x-axis. Sorry, not x equals 0 line, but around the x-axis, right? Because the graph of f of x was symmetric around y-axis, graph of f inverse x is symmetric around x-axis. Okay, so this is how we can draw the graph of a function and its inverse function. I can give you some more exercises that you can try at home. More in class exercises. So first, draw the graph of x cube, find its inverse, and draw the graph of its inverse as well. find inverse and draw graphs. You need to do that for all these problems. Let's say another function is f of x equals to 1 minus x square. Okay. Another graph is 1 by 2x plus 1, right? So do it for these three. Okay. All right, so I will stop here. This is it on inverse functions and how to draw the graph of a function and an inverse function, and how to find out domains and codomains. So by the end of this lecture, you should be confident at drawing the graph of a function, how to find domain and codomain of a function, and how to find inverse of a function, because these are very useful toolkit that you will require later on in this course. And this is the fundamental building block for functions. So once you understand functions, you will be able to understand calculus and also probability, right? So it will become easier. Right? So although this is slightly challenging, but if you practice, you can do well on these parts. Okay. All right, I will stop here. In the next lecture, we will start logarithmic functions, which are an important types of functions that we use in cognitive sciences as well as other natural sciences, right? So I will stop here for this lecture. Thank you.